Mm, 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 mm. Hi everyone, we'll be starting in about 1 to 2 minutes time. Alright, good afternoon everyone. Hopefully you guys had a good weekend. Today's lecture is going to be on the topic of convolution. And we'll be doing basically the explanation as to how do we form the convolution integral in particular in today's lecture. Tomorrow's lecture we'll be doing more of the worked examples as to how you can apply the convolution integral in solving problems. And then the final lecture for tomorrow would be the first and second order systems and what can be expected of those with respect to the transient response and the steady state response analysis and so forth. So let's get to today's lecture in particular and let's see how do we actually form the convolution integral in the material presented here. So, to come back to one of the most important properties of the Laplace transform, the thing about it is that we need to go back to the time domain a little bit. And we know that from our previous lectures that we would have had an x of t input continuous time signal here that would have gone into a system which would also be represented by an h of t equation, or its time domain equation. And the interaction of x of t with h of t here will produce or process output signal here in continuous time being y of t. The interaction here between x of t and h of t, many people think so far that it is a multiplication of the two signals, but it is not in the time domain. What it is actually is a convolution of the x of t and h of t signals. And then, because we operate in the Laplace transform of y of s, it means that in the Laplace transform, or the S domain, this is actually a multiplication of the h of s signals and the x of s signals in particular. And this actually forms one of the most important properties of the Laplace transform, which we will see in the last slide of this lecture. But for now, let's actually observe how do we obtain y of t in terms of x of t here with respect to this block diagram. So, we need to recall how did we obtain a sample signal in particular. So we know here that basically we had our impulse train here, which is p of t, and then this impulse train here will have multiplied by our x of t signal, which will be our input continuous time signal, produce our xp of t signal, which will be our sample signal accordingly. So this comes like we take this arbitrary x of t signal here, and we multiply it by our p of t being our impulse train, and then we basically sample the continuous time signal x of t at certain time points here, accordingly, which are spaced t seconds apart, and we have obtained our sample continuous time signal here, which have been a result of a discretized time signal. So, because h of t in this case was the impulse response or weighted or impulse train in particular, let's say in this case, if we say x of t here for this particular case was an impulse for delta of t, and we know y of t was basically h of t convoluting with x of t, the end result will mean that if we convolve with a unit impulse, we will just obtain our h of t signal here for y of t. So the convolution of an impulse with any other signal in continuous time will just result in that original signal that was there to begin with. So it will be h of t here only. Similarly, if we had x of t here being a shifted impulse, meaning that we delayed it or advanced it by capital T seconds here, and then we convoluted accordingly with that same h of t signal, the end result would have been that we have obtained an h of t signal being shifted by t seconds accordingly as of such. And also, if we amplitude scale it and time shifted it accordingly, the amplitude scaling and the time shifting here will be applied to the h of t signal accordingly as here. And all of these properties hold true because we are dealing with linear time invariant systems in particular. If we were dealing with linear time invariant systems, all of these properties here would have different effects in particular. But because this course focuses on LTI systems, these properties hold true. And they will keep on holding true for throughout the entire course because we are only dealing with LTI systems. So basically, our sample signal here, because it's a discretized time signal, is represented by x of nt, basically being a summation of the continuous time signal x of t here multiplied by our impulse train here, which will be delta t minus nt accordingly. And the summation series basically lets us manipulate it so that we shift x of t and delta of t accordingly as well. Then y of nt here, from what we have seen in our previous slide, will just basically be x of nt multiplied by h of t minus nt here accordingly. And this is what formulates us into what we refer to as the convolution sum. And the convolution sum is important for actually how do we go back into forming the convolution integral, which we'll be using to evaluate convolution in particular. One correction to the slide in particular, because the diagram here is saying things in terms of continuous time, but actually supposed to be in terms of discretized time. So this here is supposed to be x of n t. This is supposed to be h n t, and this here is supposed to be y of n t. So I'll fix that accordingly when I'm doing the revised slides in particular. But what this basically means is that for any discretized system, the y of nt signal that we obtain here from the x of nt signal going towards a system h of nt will just basically be x of nt multiplied by h of t minus nt, all in between negative infinity to positive infinity accordingly here. And this is actually what forms our convolution sum in discretized time. However, we need to know how do we evaluate this for continuous time instead, because that's going to be the basis for what we're doing in this entire course. So, in evaluating that summation equation that we just now saw here, in the real world, what actually happens is that, yes, we'll have an x of t signal here, which is some arbitrary continuous time signal, but our impulses here are mathematically, because they occur instantaneously at a point in time, that's the ideal situation. But in the real world, this actually cannot happen. So what happens is that we have a series of rectangular pulses where the width of the rectangular pulses are really small to simulate something close to an impulse. So in approximating the continuous time signal, we use this series of rectangular pulses here in order to obtain our sample continuous time signal, resulting in our discretized time signal as the result here. So in doing this in particular, this is what we refer to as staircase approximation, where the smaller the width of each one of these rectangles, you get a better estimate for the entire signal itself. And each rectangle here mathematically is defined with a height of 1 divided by delta, and the width of it here is in between 0 and delta accordingly. And the entire signal is referred to as common delta, capital delta of t, multiplied by capital delta. And yes, the math looks very abstract, but I will explain actually what it means at this point in time. So basically what this just means is that this is actually how we mathematically represent the rectangular signal here for this particular application. And it's possible for us to shift this rectangular signal, like if we were shifting a unit impulse, by also doing this with respect to k delta and k plus 1 delta accordingly, to represent each one of these rectangles here by an index of k. So for any rectangle in particular, and because these rectangles basically represent our real-life impulses, this allows us to obtain an equation here for x of t accordingly, represented by this mathematical equation here, which looks a little bit complicated, but basically what it just means is that for any one of these rectangles, because we know what k index is, that means we can obtain the actual x of t signal accordingly, or the instantaneous value of x of t at that particular point in time, represented our sample signal. And if we sum all of these rectangles accordingly and represented by a summation series, we'll end up getting this summation equation here as well, which basically represents the summation of each one of these rectangles sampling the x of t signal here, which is a continuous time signal, to form our discretized signal x hat of t accordingly. So in doing all of this, basically, let's say if our x of t signal in this case was what our staircase approximation here for one of those rectangles that we just now saw, represented by delta delta of t here. In this case, as we saw in the previous slides, once we convolve with an unit impulse, we'll just obtain our h of t signal here accordingly as of such. And because we're also doing this for x of t hat and y of t hat here accordingly, the same property holds true accordingly for when we move in throughout the entire system. So the x of t hat signal will have the same evaluation as if we were doing it for the summation of all those rectangles that we just now saw. And when we apply it to our y hat of t signal here accordingly, basically, it just comes like if we're just multiplying by the x of k delta signal here. And this delta delta signal here now becomes h delta accordingly with the same time shifts as well. And these properties only hold true in particular because we're dealing with linear time invariant systems. Now, in order to approach the convolution integral from using a real life example here, remember the reason why we have k delta is that we're actually using this as our actual physical width of the rectangles that we just now saw that represent our impulse signals. So capital delta here basically represents the width of those rectangular signals. And basically, the smaller that width is, we get closer to the actual mathematical realization of what a unit impulse is. Because remember, a unit impulse mathematically is just a concept, because we're saying that occurs instantaneously at that point in time. And if you can also remember, a unit impulse mathematically is defined as having 0 width and infinite height. But in the real world, we can't have something having 0 width. So the reason why we have capital delta there is to represent that really small width that we use for those rectangular windows while we're summing. Now, in order to approach from this equation here, which is our real world signal equations, to get to our actual continuous time equations, this happens where we actually have to apply the limit as the width of the rectangles here approach 0 to move towards our actual ideal unit impulses. And in applying this limit here, as delta tends towards 0, that means all of these signals here also change accordingly as of such. So our xk of delta here now becomes x of tau accordingly in applying this limit. Our h delta of t minus k delta here multiplied by that same rectangular width here now becomes ht minus tau accordingly, and this delta here becomes d tau accordingly. And this limit basically comes like if we were doing the same thing when we were applying the first principle differentiation that we saw a couple of lectures back, where if we did the differentiation between 2 points, we had the difference in y divided by the difference in x. And we also saw that in applying that limit there, we moved from that difference from being delta of t into also a dt signal. So for this case here in particular, this capital delta that we see here moves towards d tau because we're moving from discretized time being a summation series to continuous time, which is represented by an integral form here instead. So the limits of the summation series here also transfer over to the integral evaluation here. So it goes from negative infinity to positive infinity. The x of k delta signal, because we say delta tends towards 0 in the limit evaluation, becomes x of tau. And the h delta t minus k delta here becomes h of t minus tau accordingly. So anything that was k delta becomes tau in particular. Anything that was t remains as t as of such. And because we have the delta on the outside here as well, this actually represents our differential here being d tau here as well. And this integral equation that we're seeing here in particular is what we refer to as the convolution integral. And this is the equation that we're going to be using throughout the entire course to evaluate all forms of continuous time convolution. And in the next lecture in particular, we'll be seeing how we actually apply this equation to some worked examples that I'll be doing in class itself as to how we actually evaluate convolution between an x of t signal and an h of t signal accordingly as of such. So just keep in mind that this equation here is going to be very important for when we're actually doing convolution problems, especially in the next class in particular. And this equation is what we refer to as the convolution integral. So, and returning back to our original question here, I need to fix this as well. Put a note on the slide. Right. So basically what this equation is supposed to be is that in the Laplace domain we had y of s being a multiplication of our h of s signal here and an x of s signal, where the h of s signal would be the Laplace representation of h of t here, and the x of s signal would be the Laplace representation of the x of t signal here as of such. And doing our convolution here, because in the time domain this interaction between x of t and h of t is actually our convolution, and it's represented by the convolution integral form here. The shorthand version of writing the convolution integral is just saying x of t star h of t. Not multiply, star. This is the shorthand version for writing the convolution integral. The most important property of the convolution integral here in particular is that the convolution in the time domain, which we see here represented by this integral form, when we transfer this to the Laplace domain, it's actually a multiplication in the s domain. So x of t star h of t would give us the same result as if we say x of s multiplied by, h of s multiplied by x of s here accordingly. So convolution in the time domain, you don't always have to actually do this respected integral form here. You actually transfer your x of t signal into x of s and your h of t signal into h of s here accordingly, and then do the multiplication in the Laplace domain between x of s and h of s here. And once you obtain your final equation, you can then partial fraction it, do your inverse Laplace transform, and once you get that result, that actually represents your y of t signal here as accordingly. Because remember, the multiplication of h of s here and x of s here gives us our y of s being the Laplace representation of y of t here. Alright, so today basically was a very short lecture with respect to convolution, because this is just basically giving us the mathematical explanation how we move from the real world signals to the actual mathematical representation of the ideal signals for convolution. And in particular, we saw that in doing all the approximations using the staircase approximation signal that we just now saw, and applying the limits accordingly, we move towards from this convolution sum to the convolution integral here that we'll be using throughout the entire course. And the most important property of the convolution integral, or any convolution in particular, is that a convolution in the time domain represented by this integral form here is similar or is the same as if you converted the x of t signal here and the h of t signal here into the Laplace domain equivalents and just multiply the two in the Laplace domain. As after you multiply the two, because this is going to be a y of s signal here, you can then partial fraction the equation and then do the inverse Laplace transform to get back y of t here accordingly as of such. Alright, so are there any particular questions for what we did with respect to convolution here? So we have a question here asking, is convolution like a way to test the system's response to certain inputs and show it in the time domain? So yes, that exactly is what convolution does. It's basically you're subjecting your system h of t to input signals x of t here, and you're trying to figure out what is actually going to be the system's response to that x of t signal. So yes, it's actually that. And it's defined in terms of the transfer function accordingly if you're doing it in the Laplace domain. But in the time domain, it comes like you're doing the integral evaluation, which gets a little bit tricky. And you'll see that in particular when we start doing example problems as well. But during the example problems, I'll also explain like what to look out for and how to actually do the convolution step by step to actually evaluate it properly as of such. So yes, it is basically a way to test the system response to certain inputs and to see the effect of it in the time domain. So what convolves intuitively means is basically that you're trying to slide one signal on top of the other while holding the other signal stationary. It's like visually, when we start doing examples, you'll see what the process means when we're talking about convolution, and because it's basically a sliding process, and once you visually see it, you'll understand it a lot better, especially when we're doing the worked examples in tomorrow's lecture. Convolution is not to be confused with encryption or decryption in particular. It's not really cryptic. It's more of how do we actually apply filtering processes in particular. Because from your electronics lectures that I understand, most of the time when you're dealing with filters, you basically do the analysis in the Laplace domain. And as we saw here, is that basically in the Laplace domain, because you're multiplying Laplace signals, once you do the inverse Laplace transform, the multiplication results, you basically get back in terms of time. And that basically is like the same as if we did y of s equal to h of s multiplied by x of s. And then once we obtain our y of s equation, we then do partial fractions and inverse Laplace transform to get back y of t. What we're doing here, in particular with convolution, is that we're not going to be doing the evaluation in the Laplace transform. We're going to observe actually how it's actually done in time instead. And but particular aspects of convolution, you'll actually see where you can use the Laplace transform in particular to shortcut your work instead of doing this long integral form here that we're observing as the convolution integral. So basically what we want to observe here is how we do the analysis of these signals with respect to time only. And if it's possible, we also can do the analysis of the signals using the Laplace transform instead to shortcut our work. Oh, you meant figuratively. Oh, okay. But yeah, basically it just means that you hold one signal stationary and then you use the other signal and you slide that other signal on top of that signal and observe the result for each slide. And it's basically is the formation of how your electronic filters work in particular. Right. Any other questions in particular? Alright, so it doesn't look like we have any further questions with respect to the convolution lecture in particular. So what I'm going to do here is that I'm going to go towards the questions that we had for the last previous lectures, and we're going to be answering those because I promise you guys I will actually answer this. So, oh no, we had one more question here in particular. Okay, so let's see what it was. Can you go over the part where you introduce the notation k delta? Alright, yeah, sure. So the notation here for k delta is basically representing how we actually, so let's see if I can get this up here in particular. Right, cool. So the notation for k delta here basically represents how do we actually shift this rectangular signal to represent each different rectangle here. So basically, if we're dealing with this rectangle here, and we say, okay, this is our first rectangle in the entire series, this is just going to be delta here accordingly as of such, in between 0 and delta. But when we go to the next delta rectangle here in particular, so let's say we went to this one, how do you actually give a unique identifier for it to be like, okay, how do we know this is the second rectangle and then this is going to be the third one and the fourth one and so forth? So this is actually where we use a k index here in particular to be like, okay, this is representing in this particular case our second rectangle. So when this is when k here is actually 1. So if we say k is 1 here, this is delta, which represents this point here on the axis. And then for the next part of the width here, this needs to be k plus 1 here of delta. So this comes like, if k was 1 here, this point here is delta, and then 1 plus 1 here will give us 2, so this will be 2 delta here accordingly. The k index here just basically represents the points on the x-axis here. Because if we watch for the first rectangle, if k was 0, this here is going to be 0, for this x point here. And then, because k is 0, this will be 0 plus 1 multiplied by delta, so this will just give us delta here accordingly. So the k index here basically just represents which rectangle you're dealing with in particular, and the x-intercepts for those particular rectangles. Hopefully that answers the question, unless you're referring to something else in particular. Ah, it's okay. Looks like we're good. Alright, so let's pull this down and let's go on to the previous questions that we had, which were our homework problems. So we're required to find or pose on zeros lecture to get the inverse Laplace transform of this particular problem here. And in particular, we can actually use, let's say, because we're doing this in practice, I'm pulling this up here for you guys to see. This is actually a partial fraction solver that we can use. And in doing our partial fraction solver here, this comes like if we say, okay, so we're going to do this being s squared 4s plus 20 divided by s to the power 4 plus 9s to the power 3 plus 38 s squared plus 66s plus 36. And basically, in using this partial fraction solver, which is automated first, you basically see that the solver basically is be like, okay, we can't factor this in particular. And the reason why we can't factor this is because I made an error here. Right, so now it should work. Wait a bit to see if it actually do it. Right, nice, okay. Right, so the nice thing about using these auto solvers is it actually shows us how we actually do these step by step. So in this particular case, let's see if I can maximize this a little bit for you guys. Right, it basically shows us all the steps here. Yeah, just fix that, man, thanks. Right, so basically it shows us all the steps like, okay, we factorize the denominator here and we get the factors here. And then we actually can do partial fractions here accordingly, and how we actually obtain each one of the components here as we keep on going. And then it actually gives you the final answer here as well for actually how you can do it as of such and so forth. So the auto factorizer here, which you guys can use for practice and to see like how you actually do it and so forth, it actually show you step by step actually how do you solve this accordingly as of such. And it's a nice tool in particular for when you're actually doing practice, for obtaining your partial fractions to see, okay, maybe if you made some step wrong when you're doing it manually, where did you make that error, and how you actually can correct it accordingly as of such throughout the entire thing. So, because we see here that we have two standard factors here of s, and then we have a quadratic factor here, accordingly in s squared. Basically what this means is that these two factors here will transform accordingly to exponent factors. But this factor here will basically you require a little bit of extra work because we want to get the imaginary components. And once we get the imaginary components here in the factor form, we then have to partial factor just accordingly as of such. Or if you use the Laplace transform table, there may be a direct transform here that you can use representing this quadratic form here as well, which I believe there actually is a transform accordingly for this. So I will post up the solution in particular for, let's see if I get this back here, right. I'll post up the solution in particular for this, but this is actually a good indicator for how you actually started doing these problems in particular. And I will actually give you like guys the working and so forth for this solution as to how you resolve this part of the quadratic formula itself, and how you actually obtain the inverse Laplace transform accordingly. So I will post up the solution for this later on in the week. If I don't, please remind me to post up the solution for this. Right. So I'll take care of this in particular, but the main thing I wanted to show you guys was the partial fractures calculator that you can use from SymbolLab. Right. The next problem in particular was our revision problem here, which was basically if we had this overall transfer function, we had to actually obtain what was y of t, and then what would be the steady state value, of the output of the system, and then if we had a step change here of x of t being 5 units at the input. Alright, so let's go back to our partial fraction calculator because we're going to need this to solve this. So pull this one slide here and put this here. So this is going to be s plus 3 on our numerator divided by s squared plus 5s plus 4. And our case, this actually gives us our solution right here accordingly. We'll be using. So let's bring up the whiteboard here because we're going to be using this. Right. And this. Nice. Alright, so in doing this, I'll bring this across here for me to watch. Yeah. So we had our g of s signal here. Being s plus 3 divided by s squared plus 5s plus 4. And then when we partial fraction this, we basically got 2 divided by 3 into s plus 1 plus 1 divided by 3 into s plus 4. And then if we did the Laplace equivalent of this, we know y of s was equal to g of s multiplied by x of s. And let's say x of s here was equal to 1. This is going to mean y of s was equal to g of s here. So y of t, when we do our inverse Laplace transform, I'm getting the Laplace transform tables here in particular. We basically see that this represents our exponent form here being 1 of s minus a, where the a component here is positive. So in doing this, our y of t here is basically going to be 2/3, because that's a factor on top, of e to the minus t plus 1/3 of e to the minus 4t. So that basically answers our first problem here accordingly. So what is y of t? So the next question that we had on our slide, bring this back here, was basically what would be the steady state value here of an output of our system. So let's do this evaluation with respect to time, and then we're going to do respect to the Laplace domain as well. So if we evaluate this with respect to time, this is going to be limit as t tends towards infinity of y of t. And what we are going to observe here in particular is that as t tends towards infinity for these exponent forms, and we'll have to pull up a graph here for you guys to see this. Graph sketch, I believe. So 1 second here. Right, there we go. So this function here basically represents our exponent function here being exponent of minus x. Well, let's say in this case it's going to be minus t. And we have exponent of minus 4x here. And we basically see as t tends towards infinity, we basically just approach a value of 0. So in doing this, this means that this 2/3 here is going to be multiplied by 0, and this 1/3 here is multiplied by 0. So the entire result here is just going to be 0. So yes, this is basically the final value theorem we're doing. So, but I'm showing you in respect to how we value it in respect to time first, and then how we want to be doing value with respect to the Laplace transform. So that's what if we evaluate in respect to time. Well, let's actually evaluate this with respect to the Laplace transform. So we had here that our g of s here was basically s plus 3 divided by s squared plus 5s plus 4. And we knew that y of s here was equal to g of s x of s. And for this question, we're saying x of s is equal to 1. So we're basically saying y of s is equal to g of s. And then in evaluating the final value theorem, this is basically going to be limit as s tends towards 0 of s y of s. It's going to be s plus 3 here divided by s squared 5s plus 4. And basically we can see here that the numerator will evaluate to 0, the denominator here will evaluate to 4, so we get a value of 0 here accordingly, which basically maps our two responses here in order to obtain our actual answer for the steady state with value results. And for the last part of the question, we're asking what is going to be the steady state value in response to a step change x of t of 5 units at the inputs. So that part of the question in particular, we're basically going to be saying here is that x of t here is 5 for t more than equal to 0. So what is going to be our x of s? And if we go back to our Laplace transform table here, we can see here that for any constant, in this case it being 1, this is going to be represented as 1 divided by s accordingly. So if we add 5 here, that means it's going to be 5 divided by s. But the second part, you don't have to evaluate it in both the t and s domains. I was just doing that as an illustration to show you guys the relationship. So x of s here is going to be 5 divided by s. Yeah, it's a little bit redundant, but I'm not doing it for the second part here. It's just to show you guys how the evaluation can be done either in time or in the S domain. So, in evaluating the final value theorem here, limit s tends towards 0 of s y of s, you need to remember that y of s was g of s x of s. This now is going to be y of s is equal to g of s multiplied by 5 divided by s. So in evaluating the limit, s tends towards 0 of s y of s, this will be s multiplied by 5 divided by s multiplied by our g of s signal, which was s plus 3. Make sure I'm copying this down correct. Over s squared plus 5s plus 4. These s's here will cancel. So this now becomes equivalent to limit as s tends towards 0 of 5 into s plus 3 s squared plus 5s plus 4. The numerator here, if we say s tends towards 0, is going to be 5 divided by 3. And the denominator here, the s squared here will become 0, the 5s here will become 0. So it's going to be 4. And this will resolve to 15 divided by 4. And if you want to represent this in decimal, this was to be 3.75. So that actually is the last answer for the problem if you had a step change of 5 units at the input instead for x of t. Alright, so are there any questions for that particular problem as well? Alright, so the next question here was basically for us to obtain the y of t signal and then the steady state value of the output of the system, and then the steady state value in response to step change x of t of 5 units at the input. So I'll explain why we got x of s equal 1 here for the second question in particular, and why we also put this here in respect to the y of t signal accordingly as of such. So in doing this evaluation here, the reason why we say x of s here is equal to 1 is because this comes like we're trying to evaluate this with respect to the unit impulse, at our input. So this comes like if we said x of t here is equal to delta of t. And then if you actually look on the Laplace transform table, delta of t is actually 1 in the s domain. So that's why we assume here that x of s is equal to 1 in this particular case, because we're doing the evaluation towards as if the x of t signal was a unit impulse. So And doing this in particular, because we need to obtain y of t here, we know y of s is g of s, x of s, and we're saying x of t, the input to our system is just going to be a unit impulse. On the Laplace table, the Laplace transform for a unit impulse here is just going to be 1. So as of such, x of s here for any unit impulse will just be 1. So y of s here will just end up being g of s. And once we have this, we actually can partial fraction this accordingly, because the denominator here will factorize into s plus 1 multiplied by s plus 4. I can do partial fractions to get the a and b components here, which will be 2/3 and 1/3 accordingly. And once we have this, use the Laplace transform table to obtain the inverse Laplace transform. Because it's s plus 1, it's going to be e to the minus t. And if it's s plus 4, it's going to be e to the minus 4t accordingly. On the Laplace transform table, this is represented by this transform here, transform 2 on the table. If it's minus a, a here will be positive. If it's positive a here will be negative on the exponent in time. So as a result, we'll get the components here being a and b being 2/3 and 1/3 will remain constant. So when you do the inverse Laplace transform, it will be 2/3 e to the minus t here, plus 1/3 e to the minus 4t, representing the components here, the 2/3 and 1/3, and these root factors here represented the exponent factors here. So for s plus 1 is e to the minus t, and for s plus 4 is e to the minus 4t. But the second question, which basically asks us what will be the steady state value of the output of the system. The reason why I did the evaluation in time here is just to show the relationship if we did the evaluation in time versus the evaluation in the Laplace domain. So because it's a steady state value, this means t tends towards infinity for your y of t signal. And because these are negative decaying exponents here, being e to the minus t and e to the minus 4t, when we actually plotted those signals, we saw basically as when t went towards infinity, these signals here basically approach 0. So it means 2/3 of 0 and then 1/3 of 0. And if you actually substitute 0 for these exponent values here, that we end up with an end result of 0. So this is if we did the evaluation in time. You can choose either to do it in time, or you can choose either to do it in the Laplace domain. Either way is fine, you'll end up with the same value. One way might be a little bit longer than the other, depending on how you do it, but most of the times you'll be doing the evaluation in the Laplace domain. So for the final value theorem here, it evaluated in the Laplace domain. Because we know y of s here was equal to g of s from a previous explanation, being x of s equal to 1, because it's a unit impulse in time. That comes like if we just do the final value theorem here for limit s tends tending towards 0, of s y of s. And in evaluating this, we basically see that the numerator here will be 0 multiplied by 0 plus 3, giving us 0 here. And the denominator here would be s squared plus s5 plus 4, so this s squared component here will go 0. This 5s component here will be 0, so the denominator will be 4. 0 divided by 4 will just give us 0. So that basically answers the second question. And the third question, which basically asked us the steady state value in response to a step change x of t of 5 units at the input. This means that now we're going to have to figure out, okay, we know x of t is going to be 5 units at the input at t more than equals 0. What's going to be the equivalent Laplace transform for us to get x of s? So we know x of t here is 5 at t more than equal to 0. Or what is x of s? So we need the Laplace transform table in order to obtain this. So in watching the Laplace transform table here, we see for any constant here being 1, the equivalent Laplace transform is going to be 1 divided by s. So if the constant here was 5, the equivalent Laplace transform will just be 5 divided by s accordingly. So that's how we obtain our x of s signal here from x of t being 5 divided by s from the Laplace transform table. We also know that the final value theorem was limit as s tends towards 0 of sy of s. And y of s here was basically g of s multiplied by x of s. So we know our x of s signal here is 5 on s. So now we have to substitute this accordingly into our y of s equation here. And substituting this, we now evaluate the limit accordingly for sy of s. So this s here will be here. Our x of s was 5 divided by s. And our g of s signal here was the s plus 3 divided by s squared plus s5s plus 4. These s's here on the numerator and the denominator here will cancel, leaving us with 5 multiplied by s plus 3, all divided by s squared plus 5s plus 4. And because we're doing a limit evaluation here, as s tends towards 0, this 5 is unaffected. The s here becomes 0, so the value inside the brackets here will just be 3, so you get 5 multiplied by 3. The denominator, the s squared and the 5s components here will become 0, leaving us with 4. So our denominator value here will be 4. And we just multiply out accordingly, will be 15 divided by 4, which will give us a final answer of 3.75. And that answers the last question that we had there. Right. Any other further questions? Alright, I don't think there are any other further questions. If there are any other questions, feel free to leave the questions in the comments or email me directly, and I will respond to you guys accordingly. I did promise to post up the solution for that inverse Laplace transform, so I'll do that sometime during the week. If I do happen to forget, please remind me and I will make sure I get it done as a priority. But I do have it written on here to actually complete it, so most likely I will have the solution up for you guys by the end of the week. Alright, so just remember tomorrow's lecture will be the second convolution lecture, and then we're moving on to the first and second order systems. And that second convolution lecture actually is quite important because it actually shows us how do we evaluate the convolution integral for actual signals accordingly in the time domain. And that lecture is very important, so try your best not to miss that lecture tomorrow. So until then, take care, be safe, and I'll see you guys soon. Later.